Hi, I was asked to go over a couple examples similar to the ones asked in Newton for the section dealing with exponential growth and decay. Now, for this first one, it says, suppose a disease is introduced to a population of fruit flies, and the population of flies decreases at a rate of g of t equals to negative 2 e to the 0.5 t in flies per day. If the initial population of fruit flies is 260 flies, find a function capital G of t that gives the number of fruit flies at time t. Assume that day 1 lasts from t being between 1 to 2 but not including 2. Day 2 lasts from 2 to 3 but again not including 3, and so on. On which day does the number of fruit flies reach 0? Now, one thing to remember, when we were first learning about derivatives, that if you had the population function and you wanted to find the rate of change of the population, you take the derivative of that population function. But now in this case, we're given the function that represents the rate of change of the population, and we want to find the original one, so we do what's like the reverse operation, which would be finding the integral of the rate of change function. So to find the capital G of t, what we're going to do is we're going to take the integral of our rate of change function. So in this case, that would be the integral of the negative 2 e to the 0.5 t dt. And to find the integral of this, we do a basic substitution. Let's let u equals to the 0.5 t, then du equals to 0.5 dt. So if we do the substitution, we're going to multiply the inside by 0.5, divide both sides by 0.5, and when we do that, we get the integral of, it'll be negative 4, because negative 2 divided by 0.5 is negative 4, e to the u du, which is the same thing as negative 4 integral of e to the u du, and the integral of e to the u is just e to the u, so this will be negative 4 e to the u plus c. And doing our back substitution, we get that g of t equals to negative 4 e to the 0.5 t plus c. So this would be the population function, except we don't know what c is yet. To do that, we use the fact that we know the initial population of fruit flies is 260. So we're going to use that to solve for what our constant of integration is, because we know the population at time being 0 was again 260. So plugging in 0 in for our t, what we'd end up getting is, so g of 0 is negative 4 e to the 0.5 times 0 plus c equals to 260. 0.5 times 0 is 0, e to the 0 is 1, negative 4 times 1 is negative 4, so this would be negative 4, plus c is 260. Add 4 to both sides, we get c equals to 264. So what this gives us is that our population function is negative 4 e to the 0.5 t plus 264. So this is a function representing the population at time t. So what we did again to get this is, when you have the rate of change function, if you take the integral of that, that'll allow you to find the population function. Similar to like if you know the velocity function, going backwards to get the position function, and so on. Okay, but this is not what the question asked for. The question asked for, when does the fruit fly population reach 0? So we're trying to find t such that g of t is equal to 0, that our fruit fly population is 0. So what we do is set our function equal to 0 now that we have it. So that'll be negative 4 e to the 0.5 0.5t plus 264 equals to 0. Let's see, let me add this 4e to the 0.5t to both sides. So we get 264 equals to 4e to the 0.5t. Divide both sides by 4, and let me just flip the which one's on which side. So this would be e to the 0.5t equals to 264 divided by 4 would be 66. Now to solve this exponential equation, when we have an exponential equal to a constant, what we could do now is take the natural log of both sides. We have the natural log of e to the 0.5t equals to the natural log of 66. Using a property of logarithms, we could bring down that exponent to the front of the logarithms. So we'd have 0.5t times the natural log of e, or the natural log of e is just 1. So we have the 0.5t equals to the natural log of 66. Divide both sides by 0.5, which would be the same thing as multiplying by 2, right? Because 0.5 is 1/2. So that would be 2 times the natural log of 66. If you plug that into your calculator, that'll be about 8.3793 ... So this says, so the population reaches 0 on the 8th day. So that's one application of dealing with exponential growth and exponential decay. But for these ones, like we were saying, we would take the integral of our rate function. Now another example is a stagnant pool of water is a perfect breeding place for mosquitoes. If the rate of population growth from breeding is given by b of t equals to 9e to the t plus 2t, where t is in days, and at t equal to 0 the population is 340, how many mosquitoes are added to the population by day 4? Round your answer to the nearest whole number. Okay, now there's actually a couple ways you could do this. One way is to find the population function, similar to what we were doing before, by finding the integral and then using that to solve for a constant of integration, because they do actually give us the initial population. And then we could find the population at time 4, because they say, but then that's not what it's asking for. It's not asking for what is the population at on day 4. It's asking how many have added to the population by day 4. So what you could do is then take that population at day 4 minus the initial population. So that would equal to how much has it changed. Now another way you could do this is just using the definite integral, because remember the definite integral, if we had the definite integral from a to b of a function f of x dx, that's equal to the f of b minus f of a, where capital F is the antiderivative, and that gives the net change between the population at time b to from time a. So that would be the same thing as what we were just talking about, that finding the antiderivative or the integral and then subtracting the population on day 4 minus the population on day 0. So we could just do it using the definite integral. So for this case, we'd go from the integral from 0 to 4, because we want to know what is the net change in the population from day 0 to day 4. And we have our rate of change of the population, which was that 9e to the t plus 2t, and then dt. So this would be equal to, okay, finding the antiderivative of 9e to the t, that would just be 9e to the t. For the 2t, that would be plus t squared. Evaluating that from 0 to 4. So plugging in our upper limit, that would be 9e to the 4th plus 16, because that's 4 squared, minus plugging in the 0, so that would be 9e to the 0 plus 0. So this would just be what? 9e to the 4th plus 16 minus 9. And then plugging that into your calculator, you would get that would be about 490 98.383 dot dot dot. So the number of mosquitoes that have been added, or the net change in the population, is 498 when you round to the nearest whole number. So again, that's one way. Or just to show you, we could have also done similar to what we were doing in that last example. Find the population function. So find the antiderivative of just the 9e to the t plus 2t dt, which we know is 9e to the t plus t squared, but then we have this plus this constant. This would be, let's call it capital B of t, the population at time t. Well, we still got to solve for what our constant of integration is, but we know when t equals to 0, the population is 340. So what we would do then is to solve for what c is by plugging in t equal to 0, our population is 340. So we'd have 9e to the t plus t squared, e to the 0 plus 0 squared plus c equals to this 340. Well, e to the 0 is 1, so this would be 9. So this, solving for c, we get c equals to 331. So our population function is 9e to the t plus t squared plus 331. And then what we could do is find out, okay, what is b of 4, and then subtract that from b of 0. And that'll just give you, again, this 490, well, let's just say, so b of 4, that's 838.383 dot dot dot, minus our initial, which we know is 340, which is what we'd get if we plug in t equal to 0 into here. And once again, we get that 498.383 dot dot dot. So it's actually easier doing it with the definite integrals, but just so you could understand, this is the reason why. We don't have to solve for our constant of integration, because when we do the subtraction, those cancel each other out, right? Because it would be the 331 here, the 331 here, subtract them, they cancel. So this is the way you would do this type of question, where again, when you're trying to find the net change of the function, when you know the rate of change of the function. So I hope that helps.